All right, welcome to a brief screencast about Doppler shift. This is an important concept to understand if you want to understand how scientists know, for instance, that the universe as a whole is expanding, how scientists know that certain things are moving toward or away from the Earth, things like that. And it's all done with Doppler shift. Now, in Lesson 4, I talked briefly about the fact that depending on what object is giving off energy, whether it's sound energy or whether it's light energy, if that object is moving toward or away from an observer who's picking up that energy, the waves can either be kind of squished together or spread out depending on the nature of the motion of the object. Okay, so in this simulation, there's a little dot that says S, and there's a little dot that says O. S would be the source of the waves. O is the observer. Okay, so for instance, if I want to start the emission, it's showing you that the source of the waves is now giving off waves, and you know, that could be sound, that could be light. It really doesn't make any difference because the concept is the same. Now, the source is currently not moving, and the observer is not moving either. So you see that the wavelength that's emitted from the source and the wavelength that is detected by the observer, they're the same. Okay, so there's no Doppler shift because neither the source nor the observer are moving. But watch what happens when I move the source toward the observer. Okay, you notice that when I do that, this little simulation is being kind of slow. But anyway, when I move it towards, the wavelengths get squished together. Okay? I'm going to increase the pulse rate so we see more waves. All right, so I'm going to start my emission again. And this time I'm going to take the source and I'm going to move it away from the observer. And you notice that what's coming towards the observer is spread out. Okay? So this is the wavelength of the waves that are emitted, but what's being picked up is longer than that. Okay? All right, this thing is just working so slowly. All right, let me get these guys kind of centered. There's my observer. There's my source. Okay. And the interesting thing is, it really doesn't matter if it's the source or if it's the observer that's doing the moving. If they're moving away from one another, then the wavelengths are going to be stretched out. And if they're moving toward one another, the wavelengths are going to be squished together. Now, when wavelengths are squished together, and it's sound, then that means that the sound sounds a higher pitch than usual, okay? Because shorter wavelengths for sound are higher pitches. Longer wavelengths for sound are lower pitches. This is why when a car approaches you, it sounds high pitch, and then after it passes you, it sounds low pitch. It kind of goes, meow, you know, it changes its pitch. Well, light works the same way. If two objects are getting closer to one another, then the wavelengths are squished together, and shorter wavelengths for light are on the blue end of the spectrum, so we call it a blue shift. And longer wavelengths of light, like if the two objects are moving away from one another, we call that a red shift because they're spread out more. All right, so I'm going to start the emission again and let it get to my observer. All right, now this time I'm going to move the observer, but watch the wavelengths up at the top of the simulation. Okay, what is being perceived by the observer are squished together, shorter wavelengths. Okay, that would be a blue shift because the two things are approaching one another. Okay. All right, I'm going to start the emission again. This time I'm going to take the observer and move away. Okay. And notice that that causes the waves to be spread out. Okay. So anytime that the two objects are moving away from one another, it's going to spread out the wavelengths. Okay. And remember, with light, longer wavelengths put you towards the red end of the spectrum. Okay. So scientists actually look at starlight, and they know what a spectrum, for instance, for hydrogen should look like, what lines should appear. And they notice, they'll take a spectrum from a distant star or a galaxy, and they'll notice that they see the same pattern, for instance, for hydrogen, but it's shifted either a little bit towards the red end of the spectrum or a little bit towards the blue end of the spectrum. If it's shifted a little bit towards the red end of the spectrum, then they know that the object is moving away. If it's shifted a lot towards the red end of the spectrum, then they know that it's moving away really fast. Okay, if it's shifted towards the blue end of the spectrum, it's moving towards us. If it's shifted towards the blue end of the spectrum a lot, then it's moving towards us quickly. Either that or we're moving towards it quickly. It really doesn't matter. Okay, so that's just a brief explanation of the Doppler effect. And if you are curious about running this simulation yourself, hang on, I'll pause it and I'll show you. Okay, up here at the top is if you wanted to go and run the simulation yourself, there's the web address, and I encourage you to do that if you would like. Okay, this is one of the things that helps astronomers understand how things are moving in the universe.